in the discussion of beta decay. In this lecture, we will discuss about the mass of neutrino. And in the Fermi theory, we have mentioned that, or according to your Pauli's neutrino hypothesis, rest mass of neutrino is almost zero. And the rest mass of neutrino can be determined with the Fermi theory of beta. The energy available in beta decay is shared among electron and antineutron. Or simply in some cases we will say that it is shared among electron and neutrino. And you know that with the electron it is antineutrino, and if it is positron it is neutrino. The effect of neutrino mass will be greatest near the upper energy limit E0. You know what is E0? In that, where the Curie plot would turn down towards energy axis. You can see this. This is your Fermi Curie plot. So, when you are plotting this T means that is the kinetic energy of electrons. And here we have taken the unit in kilo electron volt. And this is Np by F Z dash E. Sometimes you can take this as E0. And this is P square. So, this is the Fermi Curie plot. And of course, we are expecting a straight line graph. But if that graph has a very high resolution, you can see that at the end, that means this is the actual energy you have to get, E0. But that is the maximum kinetic energy of electrons possible. Here you can see a small deviation from that straight line path. A curve, it is actually cutting the energy axis here. And the intercept will occur at an energy which is smaller than energy corresponds to rest mass of neutrino in the extrapolated intercept of the straight line. And you can understand that this difference must be equal to the energy corresponds to rest mass of neutrino. We have already mentioned that E0 energy you have taken as it is the sum of its kinetic energy and its rest mass energy. Actually, it is the concept. And similarly, for neutrino also, its energy must be equal to its rest mass energy plus its kinetic energy. But here its kinetic energy is 0. So, always it has an energy, and in all cases from that E0, that E0 actually it is shared among electron and neutrino or antineutrino. So, you can write that total energy will be equal to kinetic energy of electron plus its rest mass energy plus kinetic energy of neutrino, or with the electron you can consider it as antineutrino, plus the rest mass of antineutrino. So, in that E0 you can see that when kinetic energy of antineutrino is 0, that term is there, the rest mass of antineutrino. Though it is very, very small, but in such a curve and with very high resolution, you can feel that. And with the high resolution spectrographic measurements of the shape of the beta spectrum, actually this was done for H3. The mass of the antineutrino is found to be less than 250 electron volts. This value, you can see that it is nearly equal to 0.25 kilo electron volt. That means 250 electron volts. So, this is the energy equivalent to mass of antineutrino, and you are nearly getting this value. In recent experiments of beta minus spectrum, the range of antineutrino mass was determined as it is between M nu means mass of antineutrino. It is between 14 electron volt and 46 electron volt. And again this concept, mass of neutrino and antineutrino are identical. That we know. The mass of a particle and its antiparticle are same. So using this Fermi-Curie plot, actually you are trying to measure the neutrino mass. And that's all in this small lecture. Thank you.